Continuing our exploration of compound variable types, we're now going to introduce structs or structures. So I typedef a new myStruct of type myStruct_t, which shall contain a single short, 6 integers all in an array, and a single long. So that structure is declared myStruct foo, and then foo.a, which is the short, is set to babe. Foo.c is set to Balboa bled blood, because it's always like I say to my wife, babe, Balboa bled blood. Anyways, foo.a is babe, which was a short, and it is now being assigned to an int, b of 1. That's going to lead to some sign extension, because it is a signed short and a signed int, so that 16-bit value is sign extended up to a 32-bit value. Then we do math on the 32-bit value plus the 64-bit value. So again, there's going to be some sign extension going on, and storing it into a smaller variable, the integer. So 64-bit value plus 32-bit value into a 32-bit storage, and ultimately returning that storage. Once again, compiled without the stack protector to simplify the code slightly. So here's what we get, and we get a bunch of new assembly instructions. So let's check them out. First, we have store half word. So half words, again, 16-bit values. That makes sense. We had a 16-bit value in this code, that short a. So to write the value babe to a, we're going to store a half word. So this is going to be a store, which stores from left to right. We've got a calculation of a memory address, and that is the parentheses saying memory address, and it is rs1 address plus sign extended immediate 12. That is the memory address where we shall store the half-word sized lower 16 bits from rs2. And again, I'm a broken record here, thanks to the miracle of copy and paste. Unlike most instructions, stores are read from left to right. This arrow goes that way. For everything else, it goes the opposite direction. And the parentheses indicate, the parentheses specifically in the disassembled output indicate that something is being used as a memory address, and there is going to be a dereferencing of memory for either reading or writing. On the flip side, there is load half word, so we're going to get something back out from memory. So this is read from right to left, so rs1 plus immediate 12, pluck a half word 16 bits out of that and store it into this register. Now, this is going to sign extend it to 32 bits. And if we're in 32-bit code, then you're done. But if you are in 64-bit code, then it will further sign extend it up to the full 64-bit size of your 64-bit register. Broken record, once again, this instruction is read from right to left. And because there's parentheses, we know that it is using memory. Then we picked up another instruction, add W, for add word register to word register. So 2 parameters, a source 1 and a source 2. So add these 2 together and place the result in the destination. But the key thing here is this is an RV64I only assembly instruction. So it is dealing with word registers, and normally RV64I is dealing with double word sized registers. They're 64 bits. But this instruction is saying specifically, I'm in 64-bit mode, but I want to deal in 32-bit registers. So consequently, it's going to take the bottom 32 bits of RS1 and the bottom 32 bits of RS2 and add them together, yielding a 32-bit result. And then it will sign extend that to 64 bits and store the result into the destination register. And this instruction isn't going to care if there was some sort of overflow. It's just going to add them together, and there's no indication anywhere that the result may have overflown. And then there's the oh-so-conspicuous sext instruction. So sext.w specifically is sign extend word in register to double word register. So this is an RV64I instruction, and it is saying, hey, I want to treat RS1 as a 32-bit word register, and I want that sign extended and just placed into the D-word double word register destination. But this is scandalous, isn't it? RISC-V encouraging sexting? What about the children? Won't somebody please think of the children? Well, it's just that unwholesome influence of those pseudo instructions at it again. And so as a reminder, I've never actually seen this V TV show, so I have no context for what this picture is, but I can tell you it's extra inappropriate when we add that little jiggle. So let's go ahead and get rid of that unwholesome pseudo instruction through the use of chaos magic. Rewrite reality, and there we go. Nice, clean assembly. Traditional family values, no more sexting in our assembly. But we do pick up some compressed Louis, some compressed add-IW, which we haven't seen add-IW yet. Oh, wait, there it is. Add-IW down a couple assembly instructions later, and a compressed add-W. We just literally learned about add-W, and now we're picking up the compressed form. Great, hope you remember it. Well, anyways, the sexting is not sexting. It's a pseudo instruction, which is actually add-IW and this 0 for the immediate. So what is add-IW? Add-IW is add immediate to word. It's another one of these RV64I instructions where the W suffix is specifically telling us we want to deal in word-sized registers. So we've got a source, we've got an immediate, we've got a destination. So this is going to take the bottom 32 bits word size of the RS1 source register, and then take the 12-bit immediate and sign extend it to only 32 bits. Add them together, yield a 32-bit result, and then sign extend that ultimately and place it into the destination register because we're still in RV64 mode and it is a 64-bit register. So this again, like the add W, is going to ignore any sort of overflow that occurs as a result of this addition. But the key thing is that we can see that if sext, which behind the scenes is really an add IW, destination source, and a 0, it's really just taking advantage of the fact that the add IW is performing this sign extension after the addition, and then it's saying, you know what, I'm going to add 0. I'm going to just treat this as a word register, 32 bits, add 0, and then the add IW will do a 32 to 64-bit sign extension for me. So sexting is really just add IW. When we got rid of the instruction aliases, we did also see a compressed add IW, and this is the same ultimate result, but it is of course compressed. It has less bits, and so while it'll be written like destination register and an immediate, that immediate is actually only a 6-bit immediate, and the destination is both a source and a destination. So basically you're going to do RD plus sign extended immediate 6 and store the result into RD. Now there is a caveat here that RD may not be the 0 register because that's reserved. And then moving back to before we learned about sext, we had the add W instruction. We just learned about it. This is now the compressed add word register to word register. So add IW versus add W, they're all just additions on word registers. One of them is register to register add, and one of them is an immediate to register add. This is the register to register. So it is giving us a destination and a source. They are destination prime, source prime. That expands to the uncompressed form of destination plus source 2, because this is also implicitly source 1, source 2, add them together, place them into the destination register, but this is an add W, so treat those things like they are 32-bit values. So RD prime is the bottom 32 of whatever the initial RD prime value is, plus the bottom 32 bits of RS2 prime, get a 32-bit result, sign extend it to 64 bits. A quick reminder on Louis from before, Louis had a destination register and a upper immediate 20 bits, and it set bits 31 through 12 so that we could ultimately create things like 32-bit constants. Well, there is a compressed Louis that popped up in this code, and the encoding is like this. We've got a non-zero upper immediate 6, and so it gets a little more complicated because it's not just setting the upper 20 bits, it's setting bits 17 through 12 with our 6 bits there, and then it takes and it sign extends bit 17 to the rest of the upper bits, and it zeroes out the bottom 12 bits just like the Louis did before. So I think, well, let me just say quick that there is a further caveat that the destination register cannot be X0 or X2, but I think this human readable text makes it a little clearer. Compressed Louis loads the non-zero 6-bit immediate field into bits 17 to 12 of the destination register, clears the bottom 12 bits, and sign extends bit 17 into all higher bits of the destination. All higher bits of the destination being a nice generic way to say that although this is an RV32 compressed instruction, if it was executed as it is here in the context of 64-bit code, all higher bits would mean it will sign extend that bit 17 all the way up to bit 63, the maximum size for the 64-bit destination register. And so with that, we've learned way more assembly instructions than we want to, so it's time for you once again to go off and draw a stack diagram. Figure out how that myStruct T is stored on the stack. What's stored where? What order? Is it reordered by the compiler? Let's figure it out by reading the code. So go ahead and step through the code. You can see it with your instruction aliases, the sext, or you can see it without the instruction aliases, the addi, whatever is more convenient for you.